So for nonlinear separable data, what we a lot of times we do have nonlinear separable data. This is a very simple example where you have this being one class and the data points from the next class is located this way. There is not a linear way that you can separate these two. No matter which line you draw, you're always going to have some positive examples and negative examples mixed. So the idea of support vector machine is to actually since we cannot separate data in this space, let's project our data to a different space. We call it feature space. So here, if we could project this O upper to a location here, we can actually stack a plane here along the, if we say this is X and Y axis, and this is a Z axis, we can actually have another hyperplane that's parallel to this plane that will separate these positive examples from the negative examples. But how exactly can we do that? That's the kernel trick that we're going to talk about. So the idea is, as we noted earlier, we have one set of data that's not linearly separable, but if we project the data from this two-dimensional space to a three-dimensional space in this way, we will be able to find a hyperplane that separates the two. So originally we have the data is two-dimensional. After the transformation, we have data in three-dimensional space. As you can see, the data points in the three-dimensional space are constructed using the original value from the two-dimensional space. So this represents one dot in maybe this dot in this space. After transformation, it becomes maybe this dot in this in the new space, and now it's three-dimensional. So through those construction, we can actually start to find a hyperplane that separates two groups. So the idea is, but thinking about getting every individual variables, I mean each individual observations transformed into another space and then do the computation, the algorithm going to be really costly. However, remember that we made a node observation earlier that the SVM, during the training, the optimization problem is dependent only on inner product of two observations. And for the decision classification formula, the decision function that we saw earlier, which is here, it's also, again, dependent only on dot products. Therefore, the clever way of doing things is just to transform this to a higher dimensional space without transform each individual observation. Just directly apply the kernel function. As long as we can calculate the inner product in the feature space, we are optimizing this problem in the feature space. We're finding alphas that can give us the best decision hyperplane in the feature space. So that's the idea. When we need to classify a new example, again, we apply this transformation, again, directly by using the kernel function. So here we have example, the transformation function, if we apply on each individual data points, it's going to be complicated. We do all those computation. We turn a two-dimensional data point to a 1, 2, 3, 4, 5, 6, six-dimensional data points. And we do to compute the inner product, but we don't have to do all those transformation for every data points. We actually can directly compute the inner product because that's all this optimization function is dependent on. So this use of the kernel function to avoid carrying out explicit transformation is known as the kernel trick. I'm going to stop here and ask for questions.
Yeah, I'm not so sure if I understand that. If we go back to this very simple example.
Which one?
With the plus and the circles.
Oh.
And if we apply the transformation to all 4 points, all of them will move to the same space.
No. Because this point, every point is going to have, so this point has, let's say it's two-dimensional, right? So they have two things. We apply different transformations, so the effect of the transformation are different.
Okay.
So there's more examples coming up. You will see that.
Okay, thank you.
Yeah. So the point we are trying to make is we don't have to explicitly carry out this. We can just apply the kernel function directly to get this exactly the same result as if we transformed the data points. Okay.
May I ask a quick question as well?
Sure.
Would you be willing to contrast the difference between an inner product and like a dot product? Is it?
They're the same.
Oh, it's the same thing. Okay.
Yeah.
Thank you.
Dot product. So we have one vector. The dot product between the two is a scalar.
Okay. Thank you.
So the popular kernels that we often seen used is polynomial and the Gaussian radial basis functions. I will have to come back to these slides later. But you can see by observing, maybe we'll do this one by one. So polynomial, right? So to answer the question that we got earlier, why the points are not mapped to the exactly same height, is because that's using this example. So this is a polynomial a kernel. Our original data are here. They're one-dimensional. By using the original data, but introduce the second dimension, that's the square of the original data. We actually transformed the original data points from this position in the original one-dimensional space to this curly position in this two-dimensional space. We can see that on the y-axis they have different because we squared them. They going to the curve allow us to find a separable hyperplane to separate these two groups, positive and negative examples. Does this example help?
Yes, absolutely. Thank you.
Okay, great. So now we can look at the Gaussian radius basis function. So we can, by looking at this formula, you can see the resemblance of this this kernel with the Gaussian density distribution function. So what we see here, this is a data point, this is another data point. And we can see this is in our in Gaussian terms, this was sigma, the standard deviation, right? How the Gaussian radius basis function can be used to separate data. So the idea is for any data point, we can make this the center and draw a Gaussian distribution on top of it. For negative example, we do the same thing, but we do it because it's negative one. This curve going to go to the other direction. And for another positive example, it goes up. It's got Gaussian curve centered on this point, going to look like this. And we can sum them up, and then that give us this curve. And we know at this point, this dot is projected or transformed to in this new dimensional space at this location, and this dot is here and the red dot is here, we can easily draw a line here to separate the two groups, right? Another point for the radius, I have two representations here because both representations are used in practice in different implementations. The R package that we use, the E1071, used this formula. So as you can see, gamma is just the inverse of this two sigma squared, right? This is a parameter that you can adjust when using the radius-based function. So on the following slides, I want to show you the effect of gamma. In Gaussian distribution, we know when we have greater variation, the Gaussian curve is flatter. When you have smaller sigma, your Gaussian curve going to be more pointy. So this translates directly when you have larger gamma, your thing going to be more pointy, and smaller gamma, your curve going to be let's see, slopey, maybe. I don't know if that's a term. So the idea is when you apply large gamma, then this data point's effect on its neighbor effect is it does not affect its surrounding area as widely as this kind of smaller gamma. So a larger range of dots further apart from this dot are going to be affected by this dot. When you have really pointy things, that your curve may be only affected yourself and very closely surrounded a few points. So when you have gamma, your hyperplane, when you cut through this, you most likely going to end up with something like this. So you have lots of little mountains and you cut through them. So you have those isolated decision boundaries. Versus when you have smaller gamma, because the slope is broader, even shorter, this group of distribution going to impact more of the surrounding nodes, ending up having a more like shape that covers more dots in a range. So this represents a level of overfitting, and this is probably better. But again, when we need to find the best gamma for our problems, we can use grid search to find it. Okay, so far, question about gamma. Okay, thank you.